Hi friends, welcome back to our Control Systems Simplified series. Today we'll discuss about the concepts of stability in control systems. If we start defining stability, it is the response of a system when it diverges without bound from its equilibrium state upon excitation, then it is unstable. Now let's understand this with a classic example to introduce this concept. Consider a marble here and a bowl arranged as shown. First, the marble is inside the bowl. A small flick will make the marble oscillate about its equilibrium position and will eventually settle back to its original position here. So this is how, with respect to time, this is how it goes. In the second case, the marble is placed on top of an inverted bowl. A small flick in this case would make the marble fall off the bowl, and the marble would never come back to its initial position unless you take it again and place it back. So this, as time tends to infinitive, it goes out. Now let's come back to this first bowl where the marble is inside the bowl. What if the flick is so hard that it goes out of the bowl? Then it will never come back. And this system is stable, but exiting it with an unbound input makes it difficult to judge if the system is stable or not. Now, this brings us to the concept of bounded input. Okay, this is the bounded input. An input is said to be bounded if the input lies within definite limits of the system. If it is not bounded, then the input is an unbounded input. That's all. Now let's understand a few sentences based on the above. For every bounded input signal, if the system response is also bounded, then that system is stable. Okay, we normally call it as bounded input, bounded output, stability. The system is stable. This is a bounded input here and bounded output here, CFT. Then for any bounded input, if the system response is unbounded, then that system is unstable. We are making it into unstable system. Now with this idea on stability, now let's understand to the poles and zeros, which are a bit of terminology to understand the stability of a system, for which let's consider this transfer function g of s of a system with the polynomials, which is basically the ratio of two polynomials, n of s by d of s. N is basically numerator of s, and d is called as the denominator of in the s domain. G of s is the transfer function. So the equation is polynomial for numerator is bm s power m plus bm minus 1 s power m minus 1 plus and so on, b1s plus 0 divided by an s power n plus an minus 1 s power n minus 1 plus and so on plus a1s plus a0. Now the poles of the system are the roots of the denominator polynomial ds. The poles of the system are the roots when the poles are the values of s for which d of s is equal to 0. If this polynomial is equated to 0, the values of s are the poles. Now similarly, the zeros of the system are the roots of the numerator polynomial. Now if this equation polynomial is equated to 0, and then the values of s, okay, s is equal to plus 1, minus 1, something like that. So the values of s are the zeros on the system. So in the generalized equation in this above, the system has n poles and m zeros, right? N poles and m zeros. That's exactly what we understand from the system. Let's understand this with an example with a transfer function of s square plus 3s plus 12 divided by s into s square plus 5s plus 6. Solving numerator this equal to 0 and denominator this equal to 0, we get zeros s square plus 3s plus 12 equal to 0. If we solve this equation, we get zeros as minus 1.5 plus or minus 3.1225j. And solving the denominator for poles, s into s square plus 5s plus 6 is equal to 0, we get poles as minus 2, minus 3. Now, if we draw the plot of an imaginary axis and the real axis with this is a 0 and this is a 0 here. Now, in this, we shall explore the fact that location of the poles on the stability of the control system. Now, here, our zeros are minus 1.5 plus 3.12. That is minus 1.5, right? So minus 1.5 plus 3.1225. This is the imaginary axis. This is the imaginary axis. Okay, this is the real axis. X-axis is the real axis. Y is the imaginary. So minus 1.5. So this is minus, this is plus side, and this is plus, this is minus here. So minus 1.5 plus 3.1225j is here, your zeros, and another 0 is minus 1.5 minus 3.1225. These two are the zeros. And then the poles are minus 2 here. It's on the axis. Okay, it's on the origin, on the axis. Okay, at 0, when origin is 0. And then minus 3. Minus 2, minus 3. This is how we represent it. So since all these on the left side of thing, we consider it as a stable system. Now let's understand split by each case by case, in order to understand it more clarity. Then the effect of location of poles on the stability, if you take, then if you poles on the negative real axis, consider a simple pole at s is equal to minus 2, then the transfer function becomes g of s is equal to 1 by s plus 2. And this is exactly what we have. S is equal to minus 2 here. Okay. And g of s is equal to 1 by s. Pole at plot. And impulse response, if you see from here, it goes with time, the response approaches 0 and the system is stable. Because with time it approaches 0. So we call this as a stable system. Then poles on positive real axis, s is equal to 2, and then transfer function is equal to 1 by s minus 2. And here you will see s is equal to plus 2, so it is on this side. Pole is on this side, right? Now, if you see the pole is on the right side, then this is coming here, okay? And then when it reaches after some time, what happens? The response increases exponentially, and this means that the system doesn't settle and it is marked as unstable for an impulse response system. Then the poles at the origin, if you see, g of s is equal to 1 by s, and then you have it at the origin. At the center, you have everything. So in this case, the impulse response is on the straight line. If you see, the impulse response stays constant at 1 as time progresses. If the response slightly decreases with time, then it eventually settles at 0 and the system is called stable. If the response slightly increases with time, the response increases to infinity eventually and the system is marked unstable. So this response, where the slightest variation changes of stability of the system, is the response of a marginally stable system. So if the poles are at the origin, we call it as a marginally stable system. Now let's understand two poles at origin. We have seen only one pole. Then if you see two poles at origin, then we have both the poles at origin. And in this case, the multiple poles at origin, the response increases without bound, and hence the system is marked unstable from this for an impulse system. So case 4, the complex pole in the left half of the S-plane. So we get S is equal to -2 plus 3j for this equation, and S is equal to -2 minus 3j. So because of which we get this transfer function. Okay, and in this you will see S is equal to this is -2, and the imaginary axis from 0, it is 3. Okay, so -2 plus 3j. This is where it can. Similarly, -2 minus 3j. This is where, so both are on the left side, so the system is stable. By changing the transfer function in the previous script, we obtain the pole 0 plot and impulse response. We understand this. So as the response approaches to 0, as time increases, the system is stable. So here. So once it reaches 0, then the system is stable. Similarly, case 5, the complex poles in the right half of the S-plane. So we get S is equal to 2 plus 3j, 2 minus 3j. Now this is 0, plus 2, we have plus 2, plus 3j, and plus 2 minus 3j. This is minus part and this is plus part. So this is the corresponding transfer function for this. Now, as seen, the oscillation of the response keeps growing in amplitude, and hence the system response becomes unbound and unstable for the impulse system. And since the poles are also on the right side of the S-plane, we call it as a system as unstable. Then finally, the poles on the imaginary axis. The pole lying on the imaginary are purely imaginary. Consider the poles to be at S is equal to 3j, S is equal to minus 3j. So this is on the imaginary, plus 3j, minus 3j on the 0. On the 0. This is how we represent. Now the response of this type of a system is a sustained oscillation. An oscillation where the amplitude remains constant, we normally call it as sustained oscillation. Now if the amplitude of the oscillation slightly reduces, it eventually decays with time. If this amplitude slightly reduces over a period of time, it slightly decays with the time. But if the amplitude of the oscillation slightly increases, it eventually rises to infinity with time. So the condition where the response is a sustained oscillation lies in between being stable and unstable. This is exactly what we call marginally stable system. And these are all about different cases which we have seen. Now let's summarize all these things by concluding. If all poles lie in the left half of the S-plane, then the system is stable. If any pole lies in the right half of the S-plane, then the system is unstable. If the system has 2 or more poles in the same location on the imaginary axis, then the system is unstable. If the system has one or more non-repeated poles on the imaginary axis, then the system is marginally stable. So that is exactly what we have. Okay, now that's exactly about the concept of stability. Hope you have understood this concept, and thank you very much.